Recording on. All right. So yesterday I got started on a new topic, which was an alternative to linearization in order to establish stability or instability of a fixed point. And this goes by the name of Lyapunov's second method. I also gave you some motivation why an alternative is needed for two reasons, actually. One of them is that linearization can be inconclusive for conservative systems, and conservative systems are nevertheless a big area. Like I said, one application being molecular dynamics, but even in rigid body dynamics, often people resort to conservative models. And the other thing is that linearization by itself doesn't tell you anything about the domain of stability. So even though you might have an asymptotically stable fixed point on paper, its domain of stability from which it actually attracts solutions might be tiny. Therefore, what linear stability analysis in practical terms, if you're not aware of this issue of the size of the domain of stability, might even be misleading, because actually relatively small but finite perturbations can still take you out of the domain of stability. Because remember, the domain of stability always starts with a sufficient list. There is an epsilon larger than zero, such that. So it's about a potentially small domain in which trajectories decay. I give you the example which came to my mind. It's a high profile example, which is the transition to turbulence in pipe flows in general, in shear flows, where you do have, for increasing Reynolds numbers, a spectacular decrease in the size of the domain of stability. And that's why, even though on paper the Navier-Stokes equations correctly, by all accounts, indicate the stability of the laminar flow, the domain of stability becomes tiny as you increase the speed of the flow, as the Reynolds number goes to infinity. So at some point, very small imperfections, tiny vibrations in the building, anything can put you on the other side. Okay, so, and then I went ahead and started stating the first relevant results. So in principle you can get more, but you also have to assume more. And this approach is therefore not universally applicable. It will be applicable when what we call a Lyapunov function is available. I didn't use that term here, but I'm going to introduce that. It's used a lot in controls, also in classical mechanics in a probably more general context. But basically, the assumption is that for your dynamical system for which x naught is a fixed point, you can find a function which is at least once continuously differentiable in an open domain that contains the equilibrium point. And what I'll just add here is the usual terminology. The V is called the Lyapunov function. How did I spell Lyapunov with a Y? Okay, some spell it with an I. There's two different spellings, so I'll spell it like this. Here I'm assuming V to have particular properties 1 or 2 and call it a Lyapunov function, but more generally, this whole approach, when you establish stability with this, with the help of an additional function with good properties, in general, these are called Lyapunov functions because they just are being used in this alternative approach to linearization. But this is the most sort of classical theorem. So if you have a function on an open domain such that it vanishes at 0, which of course can always be achieved. If it doesn't vanish at 0, you just add a constant to it and it will vanish. It will not change the shape of the function. But then the 0 should really be at least a local minimum, and the value of 0 should be isolated, but the value of the function should be isolated from 0 on this open domain. So for all we know at this point, it can have a general shape, but it cannot come back to 0 on U. And so what we say in this case is that V is positive definite in U. And what we require, that is derivative with respect to time, and you might ask how that's done because it only depends on space, but it's the derivative in time along trajectories of this dynamical system instantaneously. So which you take by the chain rule to be the gradient of v multiplied by x dot, but x dot is f of x. So this is computable without knowing the trajectories, okay? And we require this to be non-positive. So it can be negative, it can be zero, but zero and negative, nothing else. So what we say is that v dot is negative semi-definite. Then the statement is, and mind you, no linearization, no work has been essentially performed in f other than the verification of this condition. So you just feed f into this inner product, and this has to be satisfied. And that's the only requirement we have. The only thing we need to know is that which we start with is that x naught is a fixed point. But again, that's just algebra on f. So under these conditions, x equals x naught is Lyapunov stable and non-linearly. So not just in the linearization, right? And then I made a second statement, and then I was too quick with that because we were nearing the end of the class. That was incorrect. So in fact, there's no other statement in Lyapunov's classical theorem. This is it, but I wanted to add something more practical because as I was talking, I realized that I should also speak to this issue of domain of stability because I'm promising that this approach actually does give you something about the domain of stability. But then actually Lyapunov's original result doesn't. So I thought I would quickly add something to it, but that wasn't quite correct. So let me add the correct statement. And then I'll get to that in the proof as well. So the correct statement would be that there's this domain U, remember, on which we're making all these assumptions. So I'll just make an additional assumption. So this doesn't change the conclusion of stability. So if let's just say dvx, which is the gradient of v, okay, doesn't vanish on the set, which I get by taking the closure of u. So this is an open set, right? So I'm also including the boundary of u now. So just close it, the boundary points. And take that set, but I also exclude the origin, the fixed point from it. So I just assume that this function, the gradient of this function doesn't vanish here. It must vanish here because it's differentiable and that's a minimum there. So I have a local minimum for sure, right? Because everything else is higher in value. So it does vanish here, no question, but I'm requiring that away from it, it doesn't vanish on the whole closure of u, okay, including the boundary. So just in case we are not used to this notation, then, well, maybe I put it here. So u, the closure of u by definition is just the u. Now I'm in trouble because the union of u. So this will be u union the boundary of u, the boundary points. So the boundary points of an open set are all the limit points of Cauchy sequences in that set. So just in case you forgot that we have a general definition of that. So you take all sequences of points with decreasing distances, all of them. And because it's an open set, it's not guaranteed that those, what we call Cauchy sequences, actually converge within U. So what we do, we take all those sequences and take their limit points and add them to U. And when you do that for all possible sequences within U, then you have actually added the boundary points. So these are limit points of all sequences. Anyway, so that's you. I'm sure you even had an intuitive notion of what it means to close a set. So assume that the gradient doesn't vanish that except for the origin. Okay, then I will say the largest level set of V of X contained fully in U is part of the domain of stability. Of X naught. So basically, the statement is, if I were to show it still on this figure, and I'll go into more detail of that, that it turns out that under this condition, that the gradient doesn't vanish on U, then you can already imagine that the kind of turning back that I described will not happen, right? Because anything like that in the graph of U would actually mean that the gradient vanishes at some point. So it's actually monotonically growing. And if it's monotonically growing, then the level sets of V are not only spherical around x naught, but they continue to be spherical as you move away up until you reach U bar. Now, U bar doesn't necessarily fully contain the level sets. So as you grow larger, I mean, some of these level sets start peaking out in general. But you pick the one which is the largest and still in U bar. So something like this, right? And let's just call this, what do I call this? That doesn't clash with any notation. So let's just call this W. The largest level set, and I'll squeeze it in here, W of V of X. So this will be the largest level set that is fully contained in U bar. But I made a mistake again. Okay. So that's quite remarkable if you think about it, because again, this is just an operation on V. So all you need to do is just analyze a scalar function. You check that it doesn't have vanishing gradients. There's actually a fundamental result in differential geometry that would tell you that if you don't have vanishing gradients in that region, then all the level sets of V continue to be diffeomorphic to what they were close to x naught. So you can grow them. There's no change in the topology of level sets when you have a function whose gradient is non-vanishing. So I'm using that here. So they will all be spherical. They will not be exactly spheres, but they can be deformed ellipsoids, but definitely they're compact. Okay, so it makes sense to talk about the largest one that you can still place fully, entirely in the closure of U. And you manage to do that, which is just an operation on the function. You don't need to know anything about the dynamics of the system. And this is a nonlinear system. Okay, so when you just analyzing the scalar valued function, you find its largest level set still in U under these conditions, then you can rest assured that that is certainly in the domain of stability. The domain of stability generally may be larger, but this is certainly an estimate for that. Okay, and this is not something you get from linearization. And my apologies for the oversimplification. U itself is not generally not in that I'm working in. It's not in the domain of attraction. I mixed up U with this W. Okay, again, this is my own amendment to Lyapunov's theorem, but it comes out very easily once we understand the proof of Lyapunov's theorem. So I'll give you that. So that you won't find this, I think, in classical books, but it's just an easy addition. It's no big deal, right? So let's see if are there any questions about the statement of the theorem. And I don't have too much time to do proofs in this class because then, it would cover very, very, very little. But I think this is instructive. Any questions about the statement? So let's get into why this is true. So I think I stated everything. So it starts out with working close to U. So select epsilon bigger than 0 small, which will be basically a radius around x naught. And if it's small, then it makes sense to define a number, epsilon, the function of epsilon, alpha, which will be the following. It will be the minimum of this function, the Lyapunov function, taken over a small ball. Centered around x naught. So the epsilon and x naught is an open epsilon ball. around x naught. Okay, so the picture that will go with this, I have somewhere here the fixed point x naught, and I will then draw a ball around it. Okay, so this will be d epsilon, and this would the boundary of that. And if so, I will keep this very small because I'm not yet assuming anything else. I just go for the statement of the first. I'd better number these. Sorry. So that's the statement number one. I'm going for the proof of statement number one. And I can find a small enough ball around x naught. I can always find one which is, you know, full in U. Okay. And what I'm talking about, what I'm defining here is this alpha epsilon, which I'll just take sort of frame here. That is the minimum of V on this. So there will be somewhere a point, let's call it x star, where that minimum is achieved. So x star, of course, depends on epsilon. So what distinguishes that x star is that if I evaluate V at x star, and again, depends on epsilon, because depends on which sphere I pick there, then that's precisely alpha epsilon. So that's where you pick the minimum. So if you look at all other points in that sphere, nobody says that this is a strict minimum. So some of them may have the same value of V on it as x epsilon star, but certainly none of these points will have a lower value than alpha epsilon, lower value of V. Okay. So I think I said everything about this, and fine. Okay, then the next step is that define the following set. This will be another set U epsilon, which contains all points from U. In fact, I can be more specific, all points from this ball, such that Vx, and I evaluate V at those points, is less than alpha epsilon. So what's happening here is I'm looking at inside this sphere, and I can even look at the surface of the sphere. I could, you know, take the closure of that, and I'm asking what are the points where the Lyapunov function V has a lower value than this one. Now, mind you that this set U epsilon cannot have a single point here on the surface. Reason is that this was the minimizer of V on that surface. Nothing gets lower, no V value gets lower at any point here. So I'm free to define this U epsilon subset of the epsilon closure, okay? But I know for sure that if this is not empty, it will not reach the surface of the sphere, because if it did, then it would contain a point whose V value is lower than the minimum of V values on that surface. And that's not possible because that's how we define the minimum, right? But of course, that brings up the question, this U epsilon potentially may actually be empty. Is this a set that's empty? The claim is that it's not empty. Why? Because at least there's one point that I can immediately say is in U epsilon. Well, that's the equilibrium itself, the fixed point, because at that point, V had a zero value, right? And everything here, when I'm still U, has a larger value then. That was an assumption. That's the positive definition of V on U. So I can with certainty state that the fixed point is in U epsilon, and that means that U epsilon is not empty. It's not the empty set. But I can also say that by definition, since it's defined by a strict inequality, if it's non-empty, then it's certainly an open set. Why is that the case? Well, then points very close to x naught. There will be points that are very close to x naught. They are tiny numbers. They have tiny numbers of v on them because v is at least C1. So those will, when I pick them very close to x naught, and they will also satisfy this bound, right? So U epsilon is open. So that means that U epsilon is an open set, potentially disconnected. But what I can now already start drawing, I can imagine it's potentially disconnected, but which means that it's a collection of open sets. So maybe it has a component here, maybe it has a more elongated component there, but surely it will have one component here which contains x naught. Okay. So based on that picture, one of the open, let's just say, the open connected component of U epsilon containing the fixed point has a small ball. Let's call it B delta epsilon in it. Well, it's not a very mathematical statement, but I think you get what I mean. So what I mean is that, let's pick a different color here. I know that there's an open component of this set that contains x naught, and it's open. So that means that I'm able to pick a ball around it, which is fully contained in that component. So that ball will be what did I call it? B delta. And since I'm showing the boundary of that, I would just say that B delta bar. Okay. So that means that I started out with an epsilon, which was small, but otherwise arbitrary. So if one epsilon works, then any smaller epsilon works. Okay. And for that epsilon, I presented a logical construct that leads to the choice of an even smaller ball, delta. And that delta, B delta, and that delta depends on epsilon because my whole construct depends on that. So I'm working towards proving the Lyapunov stability because that requires that I pick an epsilon ball, which I have done here. And then I locate the delta ball so that if I start from that delta ball around the fixed point, remember that's the definition of stability, then I'm guaranteed to stay in the epsilon ball. I'm working towards that. So I have a candidate for that delta ball. So what I need to do now is actually argue that if I indeed start from that ball, the little one, which I have constructed based on this argument, then I will be contained in the larger ball forever. So clearly this is the point where I need to use the assumptions of the theorem. So note, if I now pick an initial condition, which is in this smaller ball, okay. And since technically, I don't know how I stated the Lyapunov theorem, but it was a less than or equal to, if it was a closed ball. So let's just close it like that. Okay. It makes no major difference here. It's just a subtlety whether I defined it that the initial condition has to be less than delta or less than equal to delta. I think less than equal to delta. But if it's less, then you just remove the closure from here. So if I pick that initial condition, then one thing I can say is the following, that if I then keep checking the Lyapunov function along the orbit that starts from that initial condition, and I go here now to my assumption, which is here, and that tells me that that Lyapunov function, no matter where I am in U, so I mean certainly in U because all this is inside U now, that Lyapunov function cannot grow. So this means that if I start from that point, then this will be less than or equal to V at the initial point. Okay, and that's just assumption I, double I, which was here. Okay. But then one thing I can immediately say that whatever that value of the, let me throw this up and just show where my initial conditions, I need a new color maybe. So this was my initial condition here, x naught tilde, and I'm launching a trajectory from there, okay, in B delta. So whatever that was, by definition, since I'm taking it from the U epsilon set, therefore its V must be less than alpha epsilon, because that defines the set from which, the larger set U epsilon from which I've taken it. And this is kind of these are the various components of U epsilon. Again, I don't know if it's connected or disconnected, so let's assume the most general case is disconnected. But all of these connected components are open, they are inside the sphere. And hence they are less than alpha epsilon, so that's just the definition of U epsilon. Okay, so now look at what I got, and this is for all t in forward time. I start at 0. Okay, so that means that the trajectory starting from here, it can do many things, but it cannot do one thing. It cannot ever reach this sphere. Why? Because if it did reach that sphere, it would be crossing that sphere. Okay, and at that point, its V would have to be less than alpha epsilon, right? Strictly. But alpha epsilon was the minimum along this. There's nothing that's lower than that. So the trajectory cannot cross that sphere. Right? So the conclusion is that xt x naught tilde cannot cross delta B epsilon for any t larger than 0. And now comes the geometry of this delta B epsilon, which it was spherical. So that was important, right? So the sphere, if you cannot cross the surface of a sphere, then you're doomed to stay in the interior of the sphere interior of sphere, which is that ball forever. Okay. Okay. And now for the second statement. So, which is statement 1 holds. Once we have this construct, as for the second statement, which is about the domain of attraction, we now understand this construct. And the question is, what is the notion of domain of stability? Well, the notion of domain of stability would be, is that how can I increase this external sphere that's supposed to capture the trajectories? To what point can I increase this? Because certainly I can do this for small epsilon near the minimum, but as I keep growing it, what can go wrong? The original definition of stability doesn't say anything about that. So this is more of a pushing it to its limits. So what can go wrong? Where various things can go wrong, the topology of V is changing. So it's no longer confining. So the level sets of V, they're not, so the values of V are not growing monotonically. I don't have spherical level sets. But if I do keep having spherical level sets as I move away from X naught, then what I can actually just do is that instead of selecting an exact sphere in my construct here, which actually, if you think about it, that never played the role that this is exactly a sphere, but played the role that this was spherical.
diffeomorphic to a sphere, but I never actually made any use of the fact that the radius at any point, the distance is the same, right? So what I could do then is I could replace this by a level set of V, at which point this minimum along it would not be strict, because all points would have the same value of V on it, right? For sure. But everything else would work just as well, because I never assumed that this is a strict minimum. I just assumed that it's a global minimum on the sphere. I would still go ahead and define U epsilon the same way, and I would still conclude that whatever U epsilon does, it's strictly inside the sphere. I cannot reach the surface of the sphere with U epsilon because my V value on it is lower than that constant V value that I would have all over here, right? But very important in this that the level surfaces of V must be then spherical so that they can take over the role of this sphere. And clearly I could have used the level surfaces of V locally here, but if I have no control over the geometry as I keep moving away from the origin, then I cannot keep using them. So that's what this condition is meant to ensure here, that dV is not vanishing, which is the gradient doesn't change, and just accept this fact from differential geometry that if it's never zero, then the topology of the level surfaces do not change. I go into more detail on this in part 2 of this course, but this is something that's probably believable. So the gradient is never zero. So basically, locally, actually it comes out from the implicit function theorem that locally that you can always continue part of the next level surface, you can always view as a smooth graph over part of the previous level surface when you go on. This actually one can argue from the implicit function theorem. Okay, so I have then no problem selecting, instead of an exact sphere, picking spherical level surfaces, and I can then repeat the exact same construct as long as those spherical level surfaces are fully inside U, because I am using heavily the assumptions that I have made in U, right? So this is what brings us to the idea that I can keep, the spherical boundaries role is taken over by the level surface of V, and I can keep growing that as long as I'm still fully staying within U or U bar, okay? Because at some point I'm going to be peaking out, and then my original assumptions about V and V dot no longer hold because they only hold on U, right? So this is really the whole idea of the proof. So as for 2, there's two steps. Replace B epsilon, okay, with spherical level surfaces of V, okay, locally. Near epsilon, okay, keep increasing size of these level surfaces, which is the values of V, until you reach the largest one, still fully contained in U bar. So that's what I was showing here, right? So these little ones are known to be there and spherical, but I keep growing them until I hit which basically, whichever, I don't know the exact geometry of U, but I look for the largest one that is touching U. Will be touching it U potentially at several points, but the point is that if I increase it any further, then I would get out of U bar. Okay, and that's it. So
this was a very interesting, I think, geometric idea, and that's why I went into the details of that. And basically, then the second take on this gives up on the insistence of having exactly a sphere there. Now, why did we have exactly a sphere, by the way, in the construction? Because the formal definition of stability, the formal one, which Lyapunov originally gave, insists on spheres, right? So basically, it says I can stay in a sphere, an epsilon sphere, by selecting a smaller delta sphere, right? And that was his preferred notion of stability. But of course, if you think about it, why insist on a sphere? It's a spheroid is just as good, right? A blob. I could just say topologically that the x equals 0 equilibrium point is stable, okay? If by picking a spheroid of any sort of epsilon, I can't describe it anymore with a unique radius, but hey, the largest radius, for instance, is epsilon, okay? For any such choice, I can pick a smaller spheroid whose largest radius is delta epsilon, such that if I start in the smaller spheroid, then I stay in the largest spheroid, right? So that is perfectly fine. It conveys the same meaning. That's why we can just replace the original one and still can claim Lyapunov stability. Okay, although we are not following it to the letter, but we're following it to the spirit of the definition. Then you can ask, to what point can I enlarge this construct? And then this is the answer to that. So there are similar, so some of the geometry of this. So this is sort of the end of the proof. And then let me just give the geometric interpretation of what's going on. Of the results. I'll give two in the notes, so I'm just that this is A. So this is one way of looking at it. So one way of looking at it is that here's U, and here's the fixed point x naught. And if I look at level surfaces of V, which are at least close to x naught, if I don't make the second assumption that leads to the second statement about the grad U not vanishing, then close to x naught, I will have these spherical level surfaces. So this is V of x equals constant, close to x naught. Now, those level surfaces are smooth and spherical. They have tangent spaces. So say at any point, I can draw a little rectangle, which is symbolically the tangent space at that point. Of this set V equals V naught. And what geometrically the condition assumes is that the gradient, and this is the reason why I'm working with the level set, because one thing if I want to characterize the gradient of the function, the Lyapunov function, I know that it's always locally orthogonal to the level set, and a geometric way of saying that is orthogonal to the tangent space. So what you see here is dv at that point. So if this is, say, x1, this is a dv at x1. Okay. And what I know from this condition here, which was the condition of the theorem, the second one, that this derivative of the system along V has to be non-positive. So look at how I calculate that. It's an inner product between the gradient and the vector field of the right-hand side of the differential equation. So if this inner product is less than or equal to 0, then what does that mean for the position of the vector field relative to dv? If the vector field is exactly in the tangent space, then this inner product is 0. If the vector field points outside the tangent space, and hence the angle between the two vectors is less than 90 degrees, and this inner product would be positive, but that's not allowed. So what the condition geometrically means is that I'm either tangent, or probably more likely, I'm actually pointing inwards. That angle is larger than pi over 2, which means that the vector field
at any point of these level surfaces, level sets of V, is either tangent or pointing inwards. So that's at f of x1, right? So there could be cases in which you happen to be tangent, because remember the vector field is the tangent to the trajectory. So if I imagine a trajectory right there, then it somehow has to evolve like this. So this is x of t crossing right at that point. So it forces the trajectories to be either tangent to the level surfaces of V, or actually, and that will most likely happen more like as a rule, crossing inwards. So there will be another level surfaces here, and you're also are either tangent to them or you're crossing inwards. If you just keep crossing inwards, you actually expect that you're actually attracted to x naught. But we also allow for tangency. So either tangency or crossing inwards. And that's why we can only guarantee stability, because in principle, you could keep being tangent to the level surface. So you're actually not making any progress towards approaching x naught. So that's why these conditions will not guarantee asymptotic stability, sort of on an I level, precisely because of this potential equality here, right? But this also suggests that if I make that stricter, then go back to this picture, then I will actually really have to keep crossing inwards. And then there will be another level surface here, right? And again, the vector field has to keep crossing inwards there. So that's to show that perhaps from another view. So this is the alternative view B. When I view V as a graph, the scalar value Lyapunov function over the phase space. So x1 is the first coordinate in the phase space, and well, this is all I can do. I plot x2 through xn here. So this is my whole phase space, and then I add one more dimension, and it's supposed to be straight. It's not in curved space-time. So this is going to be V, and in this is x naught here, and my V is now a cup-shaped function. This is the graph of V, right? This is the graph of V. And what happens here that is if I, take a level set of V, so basically I intersect it with what we would call a hyperplane, because it's an I-dimensional plane here. So then that intersection will come out to be something like that. And the projection of that onto the phase space here would be a closed level set. Use it. I'll just keep using to be consistent with the other picture. So this would be V of x equals V naught equals constant. Okay, so that just means in this representation is that the vector field tends to point inwards. So therefore the trajectories are crossing. Potentially there could be tangencies. Okay, but if you think about that tangency also cannot, that tangency, actually, let me correct myself. That tangency, if it's not, it either means that you're actually running on the level surface, or it means that you're touching the level surface from the inside, like so. Let me do a better picture somewhere. Because if you touched it from the outside, like so, you see what would happen. The outside level curves, when we're close enough to the origin, are also spherical. So that would mean that you're starting at this point from this level surface, and then you're moving outside, you're crossing a higher level surface, which means that V has increased. Okay, so that you cannot do. So one thing you can do, this is one thing, actually what you can do. That's not a good way of, this is the way. So you're coming in and you're actually all the others are crossing in with transversely, right? But you're crossing in with the tangency. That's the right way of saying that. But you cannot pass by with the tangency, because that would mean that V is increasing again. Reason being, again, is that there will be another nearby level surface V keeps increasing, and that would mean that you're increasing V, right? So either way, you're either crossing into the level curve transversely with an angle, or you're crossing into it, but you do it with a tangency. But you cannot, and an extreme case might be that you're just running on the level curve, because that's also allowed, right? Because that V dot will be 0. And that's precisely a possibility under our assumptions, and that would prevent asymptotic stability from being the case. But these pictures then show, so let me just say this in words, that trajectories cross inwards or remain in the level set of V. So that suggests that if I make this inequality strict, right, then I can actually improve the result. And that turns out to be the case. This is the second theorem of Lyapunov. So this was theorem 1. I go to theorem 2. So it basically says, assume the same as in theorem 1, first theorem of Lyapunov. So, well, it's not going to be the same assumption, but assume the same as in I first of theorem 1. What was that? That was about the existence of a function here, which is 0 at the fixed point and otherwise positive. I don't want to change that, but I want to fix this assumption, so to speak, to beef it up a little bit, that only allow for that. So, and assume now a stricter condition 2, such that V dot, which is still dV F, is strictly less than 0 at all points in U. Then you have two statements again, that X naught is now asymptotically stable. Okay. And 2. You get the same statement about an estimate for the domain of stability that we had here, because that doesn't change. So same W is again part of the domain of stability, and in fact attraction. So then everything in this W, which remember was the largest level set of V, fully contained in U bar, it still is the domain of an estimate for the domain of stability, but everything is also crossing that set strictly. And also if you take lower level sets of V, you're also crossing those strictly because of this assumption that I have made here. So you have no choice, actually. This needs a little bit of work, but it's believable that you have no choice but to converge to X naught. The actual proof proceeds by saying that, well, assume that despite crossing these level surfaces always, you don't end up at X naught. That would imply that you're approaching constantly X naught, but you're never reaching it. So that then you can argue that that is only possible if there was actually a surface along which V dot would be 0. That really keeps you away from it. but V dot is never zero. And then that means your only choice, this is just a little topological argument, is that you're converging to X naught. So that's a pretty powerful statement. Think about it, that no linearization is ever performed, but somebody has to give you this function, which with all these properties, but then you get nonlinear stability, asymptotic stability, and the domain of attraction estimate. Okay, so before I go for an example where we will see the exact working of this, let me just actually draw a picture here. So it's again, the geometry behind this is that the level surfaces, again, even under the first assumption are already spherical, but if you make the second assumption locally spherical, but under the second assumption, they are in fact globally spherical in U. And the reason why the proof works is that this condition tells you that you need to cross the level surfaces strictly, all of them, and you're close enough. Okay, so they're guiding you. You're basically either going like this or spiraling into X naught. That's the geometry. So this was theorem 2, and theorem 3 is that the same logic then can be, and it should be no surprise, same logic could be established, could be used to establish instability. So how would you establish instability just based on this picture? You would require a condition that actually turns these arrows to the outside. And that means that when you're starting near X naught, you're actually forced to cross level surfaces, increasing level surfaces. So can I create a condition on the, and I draw the picture already. Okay, so this will be the outcome. This will be the illustration of the theorem, right? But can I kind of reverse engineer the conditions? So this is X naught, and what I want to achieve is a setting in which when I start nearby, then I'm definitely required to go to larger and larger level surfaces. Okay, because if that's the case, then I'm done, because if I pick a small enough ball, then I'm not able to contain the trajectory in there, because the trajectory just keeps intersecting larger and larger spherical level surfaces, right? So what do I need to do then? So, well, I just need to reverse this condition. That's it, right? Because that means that I'm then crossing outwards. So this picture is no longer the way I've drawn it here, but rather df will be pointing in this direction, right? Because that inner product is all of a sudden positive. So theorem 3 would be, is that same setting, same dynamical system, and I'll just, and positive definite v of x. I need that because I need that at least near X naught, I have spherical level surfaces for the Lyapunov function for this argument. But then you assume that v dot x, which is the inner product of dv x f of x, right, is strictly bigger than 0 whenever I take x from u minus the fixed point. Because once again, at the fixed point, this assumption would fail, given that at the fixed point, f is 0. So this inner product will always be 0. Okay, so I cannot prescribe it all over u. I always need to exclude x naught. But x naught, I'm not going anywhere. There's no arrow, right? Okay, then x equals x naught is unstable. Okay, and there's one final theorem that can be useful. And that's a little bit different in nature, but the same geometric argument would show you what's happening. I'll draw the picture afterwards, because it's now a dramatic change a little bit. Is that assume the same dynamical system that doesn't change. And suppose that I have a function, like there exists, this function v, which is still a mapping from u to r, and it's c1 on u, okay? And I still assume that at x naught, the function is 0 for simplicity. But now I say that this satisfies somewhat different conditions. Now, instead of asking for it to be cup-shaped, I want it to be like a hyperbola. So it's not cup-shaped, it's not definite, but indefinite. So that just means that it takes both positive and negative values. It's like a saddle point in the topology of V, arbitrarily close to x naught. So let's assume that Vx is indefinite. In U, okay, i.e., well, actually, I said it's enough that indefinite near x naught, so it doesn't have to hold in a very large domain, because it's enough for me to establish that things are pushed away from x naught close to it. Even if they ultimately converge to something, even if they go to a limit cycle, that doesn't change the fact that x naught is unstable, okay? So it doesn't, to establish a domain of instability makes that much less sense, a little sense, because when something is unstable, it's a lost case. I can't keep it there from the point of view of practical applications, right? No matter how close I start, I'll be ejected. That's not the same for stability, because I know that, if I draw a small enough ball, I can contain it there, right? Then you can be more ambitious and say, all right, but how long that ball can be, right? The same logic doesn't apply to instability. If it's already unstable in the small, then unstable, right? So Vx is indefinite near x naught, i.e., in an arbitrarily close to x naught, there exists x1 and x2 such that v x1 is less than 0 and v x2 is larger than 0. So you get both signs for v arbitrarily close to x naught. So if you want to picture in mind, then, and again, I'm graphing V somehow over the face portrait. And again, this is really hand waving picture. And I again try to group all these remaining coordinates in the same direction. You could take, any partition, put some of them here and some of them there to make the, maybe that, your particular V requires that. Here I'm looking at the simplest case when this choice, this partition of the variables is good enough. And here's the shape that I'm after, is that, along a certain direction, you have a minimum. And some other direction, you have a maximum for V. So if I were to graph V, then it would be a surface like this. Hopefully I'm getting this right with the edges on the other side. Okay, so this would be the graph of V qualitatively. So it's 0 here, but arbitrarily close. You can find either larger values than 0 or smaller values. Okay. And I need one more thing, which is equally surprising, I think. This is kind of a new twist, but the condition is I'm not going to say that V dot is positive definite or negative definite. I'm just going to say that V dot of x is definite. Either way works for my purposes. near x naught. And then, irrespective of which definite it is, positive definite or negative definite, I will get that x naught, x equals x naught fixed point is unstable. And to get a sense why that should be the case, let me draw it here. Hopefully I have enough room. Why this is the case. Then move this a little bit, and then I get more space here. A figure. Okay. So I highlight this because this is the main result. Okay. And the geometry that goes with it is, here's x naught. And just picture the level curves, the level, these are not really level curves, level surfaces, right? But we are in n dimensions. So what I have drawn here is an oversimplification. It's not a two-dimensional surface, but that's what I mean to convey, that this is a sphere, is a hyperboloid type surface. So if I take level curves of this at level surfaces, then say I cut, at the lower level than this one, then I will get these open level surfaces, right, on both sides. If I then cut it at the right level, then I get a cross. See? So below that, I got level surfaces like this when I cut it on both sides of this hyperbole. When I cut it right at the level of 0, then I get these curves which cross each other. And then when I go over there, then I will get level surfaces like this, right? So there's a change in the topology locally of the level surfaces. So that's what I'm attempting to draw here. So there will be these sort of critical level surfaces through x naught. And again, don't take this literally because it's not really a two-dimensional example, but 2 dimensions gives you a good intuition for what's happening. And then you have one kind of set of level sets here. And then you will have another kind here. And what characterizes the red ones, although in my notes, I think I drew it the other way around, it doesn't matter. At this point, Vx is, say, larger than 0. And in these domains, Vx is less than 0. But these are still level sets. And the red ones are also level sets. And the blue ones are also, it's a single level set, but it's the 0 level set. So here you get, this is the set characterized by V of x equals 0. Okay, so what's happening here is that because V is definite, I don't know which definite. It can be positive definite, it can be negative definite, but either way, it acts as a driver. So, and it drives me just away from the origin, because suppose it's positive definite. And if I start with a trajectory here where V is less than 0, did I say that? Yes. Then it will, no matter what I do, I will have to enter sooner or later into this other region, because along the trajectory, V just keeps growing. There's nothing that would stop it from growing as long as it remains in this whole domain. Or you could say, what if it leaves the domain? Well, if it leaves the domain, then I'm done, because I started arbitrarily close to x naught and I have less this domain U, so clearly I'm unstable then, right? So as long as this stays in U, I at least have a chance to prove stability. But as long as it stays in U, it keeps then going from lower level sets to higher ones. And it doesn't have to start in the green, it can start in the red, but then it cannot go towards x naught, because look what happens, that these level sets are continuously growing. So this is, sort of very negative, then less negative, then almost 0, and then 0. And then small positive, larger positive, even larger. So because of that decrease, even if it starts here, with the positive, it can only go outwards towards the increasing level sets and not closer to x naught. So when you start in the negative domain, then this positive definiteness of v dot is actually helping you because it gives you an opportunity to get closer and closer to x naught, right? Because these level curves are larger and larger. But unfortunately, you won't be able to stop. You have to cross the zero level curve, okay? And then you have to keep growing. Likewise, if v dot is negative definite, right? And what will happen is that you will have a driver, but in the opposite direction. If you started in the green regime, then v has to decrease. So you have to go away from x naught to more negative level sets. If you started in the positive, then it seems to be working for you because the decreasing v gets you to intersect level curves that are closer and closer to x naught. But again, unfortunately, you won't be able to stop. You have to keep crossing and then you get on the other side, right? So I'll just give you one example. When say v dot is positive definite, and if v dot is positive definite, I mean, this is sort of hand waving, right? But then your overall drift direction is this. So for this picture, assume that v dot was actually positive, but the same principle applies, just reverse the orientation of v when v is negative definite. So it doesn't matter what definite it is, it's all equally bad for you and just drives you away ultimately from the origin. Okay, any questions on this? Let's see an example. And again, always the simplest example, I think, is the most insightful, the pendulum. Let's not go immediately for a multi-degree of freedom robotic arm, okay? So let's just try to see the principles at work here in a simple example. So this will be example 1. I always start with the pendulum. It's a fantastic example for everything. So the pendulum also gives you the good old pendulum, a good example for how one could actually find this v, because everything is dependent on your ability to find the v. But the good thing is that for lots of mechanical physical problems, v is some intuitive quantity that somehow governs the evolution in the phase space, somehow whose level surfaces play a role. And in mechanical systems, energy is like that. Anything that is related to mechanics. So the idea would be use energy as a Lyapunov function and see what happens. Okay, so then I just need to remind us that if this is the pendulum, so this is the direction of gravity. I have a joint here up there. This is the length of the pendulum, and I have angular coordinate phi right there, and this is the mass of the pendulum. Then the equation of motion is ml squared phi double dot. Okay, moment of inertia with respect to the joint times angular acceleration. That would be equal to the force. And we derived this already. So basically, we would have a torque acting here in the opposite direction. So the force would be negative. This is the level arm of the force. But the convention has been, let's take the negative on that force and put on the same side as the acceleration term. That's the equation of motion. Okay. And I write that out because I not without, I don't do now the non-dimensionalization because I want to talk about physically the energy. What would it be without non-dimensionalization, which is the total mechanical energy, which is the kinetic energy plus the potential energy. The kinetic energy would be 1/2 ml squared phi dot squared. So moment of inertia times, which is ml squared, times 1/2 times the angular velocity squared, right? So that would be the energy. This is a fixed point here. So this is how we calculate the sort of the rotational part of the kinetic energy. And since this mass is just rotating, This point is not translating. This is the total kinetic energy. And the potential energy will be the change in height from the equilibrium position here. And you work that out, that's mgl times 1 minus cosine phi. Okay, so this is the kinetic energy, and this is the potential energy. Okay, and this is my candidate for a Lyapunov function. So let's put things in the right context. So in the phase space, I need just to do everything by the book. I introduce one variable x1, which is phi, and x2 will be phi dot. Okay, so in the phase space, the equations of motion, x1 dot equals x2, and x2 dot equals, and minus g over L times sine x1, because I crossed out whatever I could. I simplified the equation, I crossed out L from here, I crossed out M from there. So if you then express phi dot, which is now x2, then from that equation, then this is what you get. Okay, this is your equation of motion. And then in terms of these quantities, the energy, which I propose to be, is now a function of the x, okay, because it's a function of position and velocity. And that I propose to be, I try what happens when I pick that to be my Lyapunov function. And that would be then 1/2 ml squared and x2 squared, right? This is the expression I'm working with, plus mgl 1 minus cosine x1. Okay. So the Lyapunov function in our current discussion gains a meaning and needs to satisfy conditions with respect to the fixed point of interest. So the first fixed point of interest, so at the fixed point which we have explored before and know physically that the most obvious fixed point for the pendulum is the downright equilibrium position, which is x1 equals 0, x2 equals 0. So x1, x2 equals 0, 0. I need to check whether with respect to that point, this energy satisfies the conditions that I have for the Lyapunov function. So it basically needs to be cup-shaped, and the derivative of it along trajectories, which I can compute instantaneously even without knowing the trajectories, as we have seen, that has to be non-positive, okay? So the first condition is that E at this 0, this is just x equals 0, right, has to be 0. That's not a big deal, because I can achieve that if it doesn't hold, I can just shift this function, and that will not affect. It was a point that I guess perhaps I didn't mention, that you could say, well, I say I can modify the function, but hey, maybe that has then consequences. It won't have consequences, because if I shift my original function by any constant to achieve this, the gradient of the function will not change. So that doesn't affect the second condition. That's why I just said that this is not a big deal. I can achieve that, but I certainly cannot achieve this just by shifting. But at the same time, also adding a constant to the function will not affect the second condition, right? Do I need to do that? It seems like I don't, because it's already set up nicely for my purposes. The total energy, the way I've computed it, is actually 0 here. Why? And the kinetic energy is 0 there because I'm not moving. X2 is 0. And when I plug in x1 equals 0, then cosine x1 is 1. So 1 minus 1 is 0. So I initialize the potential energy as well to be 0 there. So E non equals 0. So that's a check. That's already satisfied. No problem with that. I don't need to work, on that to make it happen. The second condition is always more challenging. But before I go there, sorry, I'm not fully done. Where did I list this? The conditions. I want to go point by point. So this is the part that's done. but I'm not done with the full first condition. There's more, right? So this is done, that's fine, but I still need to make sure that this is the case on some set U, okay? Now, physically, this is also satisfied because this is the absolute minimum of the energy, right? If I move away from this point, then I either increase the potential energy here or increase the kinetic energy or both. There's no position of this pendulum in which the potential energy plus the kinetic energy would be smaller than what I have here, right? Because once I move away, maybe instantaneously at any point, maybe, you know, if the velocity is zero, at which point the kinetic energy would be zero, because, you know, the pendulum has reached a point there. But the potential energy, certainly the way I've written it, is larger than zero there, okay? Now, that's what the physics tells you, but you are not always in a position to exploit the physics because your system might be more complicated. You don't have such a nice, simple geometry. How would you then go about establishing this point? Mind you, it's enough if the potential energy has a cup shape near x naught. So to establish that, it's enough to actually establish the curvature of the surface, that it has a positive curvature, namely that the so it has a minimum there. In other words, namely that the Hessian of the surface of the function v there is positive definite, which means that the curvatures are both positive. So in a general case, it's where you have no such clear physical understanding, or it's not so easy to visualize the surface. To establish that locally it has a cup shape, you go and check the Hessian. Well, first of all, it has to have a minimum in it. So, which is again, now I'm mixing the physics here, which we know here, but again, the way you would proceed with a general Lyapunov function candidate, you need to check first the conditions for a minimum there. So the first condition is that the gradient of the Lyapunov function must vanish at that point. So I'm taking the gradient, dE, of that function at 0. And if I take the gradient of that at 0, what will that be? Again, just to make sure we write it down, in the derivative with respect to x1 and the derivative with respect to x2. And you can check that it will be 0. We already know that the energy has a minimum, but you know, what is the type of calculation you will be performing? Here's the energy. You will be taking the gradient of this with respect to x1. And that term is not affected by that. And this is the potential energy. It will clearly vanish the gradient there because it has a minimum. And also then for the second one, you will be taking the derivative with respect to x2. Again, the kinetic energy is quadratic in x2. Clearly, when you take the derivative with respect to x2, you will get constant times x2. So when you set x2 equal to 0, that will be 0 as well. So that's going to be a check because the energy has a minimum there. But again, if you didn't know that this is the energy and someone just gave you this candidate, then you would have to go and check these one by one. And the next thing you would check is whether you have a local minimum there. And for that, you need to calculate the Hessian. So the second derivative, the Hessian matrix associated with E, which is nothing else but the Jacobian of the gradient field, would be the derivative of E, the second derivative with respect to x1, then the mixed partials, same here, it's a symmetric matrix, and then again the second derivative with respect to x2. I put the square in the wrong place here. Okay, and this needs to be positive definite. So let's see what it is. Let's actually move it slightly so that I can write out what it is. This matrix there, again, you need to take the second derivative of the energy with respect to x2. So 2 comes down, cancels this out once, and then this disappears. So it ends up being ml squared, right? And then there's no mixed partials because there's no mixed terms. And when you do that to the second one, it's ml squared. At that point, I've already plugged in the lower point. And this is positive definite. So therefore, that's a check, because there will be a neighborhood of x naught in which this has a cup shape, this function, because there's a local minimum there. And that neighborhood can be taken to be u. On that, the theorem is applicable if the second condition checks out, which is about the derivative of the energy. So what this establishes so far is that E is positive definite on some u set near x naught, which has to x naught is in u. Okay, now comes the second condition, right? In which you need to check the derivative of E. So E dot, which again is the derivative of E along trajectories, and we've discussed that this is the gradient of E, and you take the scalar product of that with respect to the right-hand side. Now the right-hand side, in this case, was this function here. This is f of x, right? So if you take this inner product, then just to write out what this is once, all right? So this is the partial derivative with respect to x1 times the first component of f1 plus the partial of with respect to x2 times the second component of f2, right? And if you write this out, then you get mgl times sine x1. I'm working with this energy here. Take the x1 partial, that's mgl, this is out, and the partial of cosine x1 is minus sine x1. So that's how you get mgl sine x1. And you take the first component of f1, which is x2. Okay, and then you take the partial with respect to x2, and that's just mgl x2. So that comes from this term here. And then this is f2. So I write minus g over l sine x1. And if you look at what we got here, they cancel out exactly. So this is dead zero. Are we surprised? No, because energy in this system is conserved. There's no damping, so you're not going to lose energy. So energy will be constant along trajectories. We anticipated that, but actually physically, but it's good that it checks out mathematically. So this is then a subcase of E being negative semi-definite, because being constant fits into the definition of being negative semi-definite, right? It's just this special case. So E dot is negative semi-definite. Although if something is zero, you definitely don't naturally think of it as negative semi-definite, but technically it is negative semi-definite. On the whole phase space, so if it's like that in the whole phase space, then certainly it will be negative semi-definite on any u that you pick, okay? So therefore, by theorem 1, x equals 0 is Lyapunov stable. And that removes the annoying earlier result that when we, even though we know the answer, right? We know the phase portrait of the pendulum and all physically we know it is stable, linearization just wouldn't buy us that result. Because if you linearize the pendulum equation at its lower equilibrium position, then you get purely imaginary eigenvalues with negative real parts, with zero real parts. So linearization does not enable you to reach this conclusion, okay, for the nonlinear system. But this is the strength of the Lyapunov's second method. There's some, if you find the right the Lyapunov function, you already have a conclusion about the nonlinear system, right? Even though, so linearization would be inconclusive. Okay. Now, what about the domain of stability? So the domain of stability, this will be an illustration. We actually happen to know the phase portrait of the pendulum. So we know that it looks like this, right? We discussed it a few times over. So this will be 0, 0. And these points will be 0, pi, pi 0. And there's another copy of that at minus pi 0, which is physically the same. And we know, I'll remove this because it's kind of in the way. We know that the level curves of the energy on which trajectories actually move are like this here. Maybe I draw one more. Okay. Now, if I were to have, if I didn't know this, which I already know from various considerations, and if this wasn't a mechanical system so that I have enough intuition, or it was a more complicated mechanical system so that I don't have enough intuition, then all I would have at this point, since I don't know the solutions and I don't know exactly what they do, all I have at this point is the Lyapunov function. And the Lyapunov function is the energy, okay? And then this would be a higher dimensional picture, for instance. So what if, even if I draw the level surfaces of the Lyapunov function, I would not immediately see what the trajectories do. I would just see the level surfaces of the Lyapunov function. Here, I'm lucky because the level surfaces of the Lyapunov function also one-dimensional coincide with the energy. So what I'm seeing here are also the trajectories. But let's just see if this is consistent with everything that we discussed. I mean, excuse my asymmetry in these. So these should be, you know, these should have the same nice distance. So if I picked, just for argument's sake, for a second, in my construct, U to be this one, okay? Now, on this U, it is true that the mechanical system has, the Lyapunov function has a minimum here. All other values of the energy are larger than this. So when you look at Lyapunov's original theorem, this is a perfectly legitimate choice for U, because on this U, the only zero value for the Lyapunov function is right here, the origin. I needed one more thing for Lyapunov's first theorem to apply, which was that the Lyapunov function had to be non-positive definite on U. But we have just concluded that the Lyapunov function is non-positive definite on any part of the phase space. So definitely it would be non-positive definite on this U as well. So for this choice of U anywhere in the statement of the theorem, I would get that the origin is stable. However, can I then apply the second part of the statement and conclude that U is in the domain of stability? If I could, I would have a problem with that statement, because you see what goes wrong here, right? This is certainly not in the domain of stability. These trajectories, they go as far away as they want from the origin. So U should not be a good estimate for the domain of stability. So what fails here? What fails here is the condition for that part of the statement. Remember what that was? Is that U had to be such, in order for me to use it for a definition, for a construction, for an estimate for the domain of stability, U had to be such that the gradient of the Lyapunov function should be non-vanishing on it. It will vanish at the equilibrium in question, but outside. Now, does the gradient vanish here? Yes, it does, because these are other fixed points. They're also in U. So that second statement of the theorem that I added to it is violated for this choice of U, because grad V or grad E fails here, right? And you see that the geometry of the statement that I made, that it's precisely these points where the topology of the level surface of a scalar valued function changes. You see that here. Up to that point, the topology of the level surfaces is spherical. Here at grad V, there's a bifurcation, so to speak, in the level surfaces. They've been break up. That's precisely what happens in higher dimension as well. Not necessarily in the same way, but there will be a change in the topology of the level surface. They are no longer spherical. So what would then be a good choice for me to apply the second statement? I could pick a U anywhere here. And a U open set. And now I'm actually doing that. So let me pick a U. So I pick some U here inside these separatrices. And it really doesn't have to, at this point, coincide with the level surfaces of V. But what I need is that the largest level surface of V actually make it so that it actually touches it here and there, okay? So this will be W, would be the largest level surface of E equals V within U. So this is my U. And it would work. Any choice of such U would work. And then the statement is that W is in the domain of stability. So it's a good estimate for the domain of stability, and C it is, right? But if it is certainly in the domain of stability. But if I picked U once again on this domain, then everything else would hold except that the gradient of V would not be non-vanishing at domain. So I could not make this conclusion. And indeed, that would be a bad conclusion in that case, because if I start points in this larger domain of U, okay, then they are leaving outside. Okay, so that is the illustration here. Any questions on this? I'm done for today. So if not, this is, again, it's reassuring. What I'm going to do next time is there's not much else I can do on the pendulum, because unfortunately, for the saddle, as I'll describe briefly, these Lyapunov theorems don't apply. So in fact, there's no such Lyapunov theorem, the second kind, which would apply here. But for the saddle, I don't need them because linearization already gives me that it's unstable. Okay, so I'll give you another example in which the choice of the Lyapunov function is no longer so trivial. It's no longer just the mechanical energy, and still then, how can you construct something, say, maybe based on physical intuition? Okay, so if there's no questions, then see you next time and enjoy the rest of the week.